Hello and welcome back. So in the previous lecture, we discussed about fatigue crack initiation and growth in aluminum based MMCs. So in the context of threshold and near threshold crack growth behavior in discontinuously reinforced metal matrix composites, it is important to analyze it in the light of crack tip phenomenon. So in this lecture, we are going to discuss about what kind of crack tip phenomena are generally observed in metal matrix composites. So in discontinuously reinforced MMCs, the crack tip phenomena that is generally found are as follows: crack closure, crack bridging, crack deflection, and crack trapping. Right, so these are the different crack tip phenomena found in discontinuously reinforced AMCs. So let us first talk about the crack closure. So as we know by now, the driving force for the crack growth is the stress intensity delta K. And therefore, any phenomenon that could shield the crack tip from the influence of the applied delta K will also influence the crack growth behavior, right? So the shielding mechanism here, if you look at the crack closure and its mechanism as to how the crack closure happens, it is primarily due to crack faces coming in contact with each other. And this can occur due to various reasons such as crack tip plasticity, oxide formation, and contact between asperities that are present on the crack surface. So this closure due to asperities present on the crack surface is also referred to as roughness induced closure. Right, so when the asperities form on the crack surface at a particular stress intensity above K minimum, these asperities can come in contact with each other, leading to crack closure. Okay. So although crack closure can happen over a range of applied stress intensity, a closure stress intensity KCL can be defined as here KCL is greater than K minimum. So crack closure will reduce the stress intensity range that is being experienced at the crack tip to an effective value, and that is what this K effective refers to. Okay, and KCl can be measured by noting the change in the bulk specimen compliance as a function of Kmax. However, KCl in itself is not a function of Kmax. Okay. So the roughness induced crack closure can be defined by this particular equation. Okay. At a particular value of K above K minimum, as per it is form and come in contact, leading to a reduction in the stress intensity range and ultimately crack closure. Okay. And the other thing that you should note over here about this crack tip shielding is the fact that the contribution of crack closure in retarding the crack growth decreases at high R. Because at high R values, large crack tip openings occur. Okay. So with increasing the load ratio, a condition would eventually arise where KCl is less than K minimum and delta K is equal to delta K effective. Now let us talk about crack trapping and bridging. So at low delta K, the reinforcement phase may act as a direct hindrance to the crack propagation by trapping the crack front close to the particle matrix interface. It has been also predicted that crack trapping on near threshold behavior will be proportional to the matrix yield stress and to the square root of particle size. Therefore, you can expect that larger particles would be more effective in reducing near threshold growth rates in metal matrix composites. And that is consistent with the experiments and the observations found in literature. Now, if you look at the behavior at higher delta K levels, here the crack growth may be reduced in composite by formation of uncracked ligaments ahead of the main crack front. So that is the crack trapping mechanism here through the formation of such uncracked ligaments in front of the main crack when it is advancing. Okay, and this bridging mechanism is attributed to the fracture of large reinforcement particles. For example, in this 7000 series aluminium alloy reinforced with silicon carbide particles, this kind of behavior was observed, and this was attributed to the fracture of large silicon carbide particles. So this particle cracking or particle fracture essentially leads to overlapping cracks. Which ultimately leads to crack bridging. Okay. On the other hand, if you have a fine particle composite, the damage ahead of the fatigue crack results in a coplanar array of bridges, right? So in one hand, you have bigger particles getting fragmented into smaller pieces, and in another hand, we are talking about a composite having the finer particles themselves. Okay. So if you have a scenario or a composite like that where you have these finer particles distributed in the matrix, then in such a composite material, as I said, the damage leads to a coplanar array of bridges formed by the crack. So therefore, you can say that fractured particles are more effective in crack bridging compared to finer particles. Okay. So therefore, particle fracture has kind of become a requirement for crack bridging phenomena. The frequency of particle fracture increases with maximum stress intensity. And with an increase in particle size as well. Crack trapping, on the other hand, arises due to the deflection of the crack around the particles. So when the advancing crack encounters the particles, since these particles are harder and stronger, the crack tend to bend around these particles, leading to this kind of deflection. Okay. So this leads to a more tortuous crack path for the advancing crack, and as a result of that, the growth rate decreases. Okay, so that is how the crack trapping will play a role in reducing the crack growth rate in metal matrix composites. So we talked about threshold and near threshold crack growth rate behavior. So now let us also talk about the mid-range growth rates. MMCs are generally found to have shown greater dependence on delta K, which translates into a higher exponent M. So if you remember, the mid-range or the Paris regime is characterized by this equation, right? So higher dependence on delta K would indicate a higher value for the exponent M. Okay. So in the mid-range crack growth rates, the values of M have been found in the range of 4.2 to 6 for metal matrix composite compared to 3 to 4 for the unreinforced matrix. And this has been attributed to static modes of fracture, including particle fracture and matrix void formation. It has been also suggested that the higher Paris exponent in composite materials is a consequence of higher apparent thresholds and lower cyclic fracture toughness, which are often observed in composites. Okay. So although the particle fracture has been usually assumed to contribute to more rapid crack growth in the Paris regime, there is also evidence that in some of the cases the growth rate may come down due to particle fracture. And the lower rates have been ascribed to crack bridging due to particle fracture, as we talked about in the case of threshold and near threshold crack growth behavior. So this was about the crack initiation and growth behavior in metal matrix composite. Now, as I would have mentioned before also, the microstructure can have a significant role on the fatigue properties of metal matrix composites. So let us talk about the effect of microstructure on the fatigue behavior of MMCs. The microstructural effects can come from particle volume fraction, size, and shape. So it has been found that increasing the volume fraction generally increases the fatigue life of MMCs under stress controlled conditions. And this is a direct result of the increased apparent work hardening due to an increase in the volume fraction of particles. But here one thing should be noted that the correlation between the volume fraction of particles and the fatigue behavior should be considered from tests done using similar testing methods, because a fatigue test can be done using different methods such as rotary bending test, axial loading test, and so on, right? So when the fatigue data is compared for a particular microstructural feature, it is always advisable that the data should be produced by using the same test techniques. Now, when you talk about the particle size, the fatigue life of aluminium-based metal matrix composites, for example, this 2124T6 silicon carbide composite, increased with increasing particle size. It can be shown from this plot, which shows the relationship between the fatigue strength and the particle size for this particular composite. So as you can see, as the particle size decreases, the fatigue strength increases. So this is for the 2124 silicon carbide composite. Although the effect of particle size on the fatigue strength is not clearly understood, but it is believed that the improvement in the fatigue strength occurs due to the decrease in the slip length as the particle size decreases. Moreover, the reinforcement particles can pin down the grain boundaries and lead to grain refinement, and therefore the improvement in the strength can also come from refinement in the grain size, which also leads to a decrease in the slip length. Okay, so both of these effects can come from the decreasing particle size, primarily due to a decrease in the slip length. Now let us see what is the effect of particle volume fraction and size on the crack growth behavior. So if you talk about the near threshold behavior, it has been found that small particles reduce the closure levels and have a detrimental effect on delta K, TH, and near threshold growth rates. And therefore, where roughness induced crack closure dominates the near threshold behavior, larger particles will give rise to a higher level of closure and hence will improve the near threshold fatigue behavior. The effect of volume fraction on the near threshold crack growth behavior is not very conclusive. While in some studies it has been found that the growth resistance increases with increasing volume fraction of particles. For example, in this composite, aluminium, zinc, magnesium, copper reinforced with 15 and 20% silicon carbide particles, it was found that as the volume fraction of particles increases, the crack growth resistance also increases. This can be shown from the crack growth plot. This is for the 30 volume percent silicon carbide composite, and this one is for 20% silicon carbide. Okay, so you can see that increasing the volume fraction of the particles has a beneficial effect on this particular composite. Okay, but for some other composites, for example, aluminium, 3.5% copper, reinforced with different volume fraction of silicon carbide particles, it was found that increasing the volume fraction has a very modest effect on the crack growth rate. Okay. Similar observations were made in some other composites also, where the volume fraction was found to have modest effect on the crack growth behavior. Now, the other thing that can be considered for aluminium based composite is the presence of precipitates, because many of the aluminium alloys are precipitation hardenable, and therefore it is good to have a look at the effect of presence of precipitates on the fatigue behavior as well. So as far as the composites are concerned, for example, if you take this composite again, it was found that aging did not really have a significant effect on the crack growth behavior. So if you superimpose the plot for the aged condition for these composites, they will come somewhere here. If you superimpose the overaged or underaged material over here. Okay, so as you could see, overaging or underaging did not have any significant effect. Same goes for the 20% composite as well. But the precipitates will definitely have some effect in the unreinforced alloy. So if you look at the curves for the unreinforced alloy, in the underaged condition it will be somewhere here. So this is the unreinforced underaged condition, and the overaged curve will be found somewhere over here. Okay, so the interesting point to note over here is that introducing the silicon carbide particles is equivalent to taking the unreinforced material into the overaged condition, at least in terms of the fracture surface roughness and the resultant roughness induced closure. Okay, so these are some of the effects of the microstructure of the composite on the fatigue behavior. So while talking about fatigue properties of metal matrix composite, you should remember one thing is that the data presented over here in terms of the fatigue behavior of composites is based on the data gathered from literature. Okay. So the important thing to note over here is that this data is neither exhaustive nor universal, right? And therefore the learner is encouraged to go through more such literatures to gain further understanding on this particular topic. All right, that's all I have for today. And now that we have covered all the topics laid out under the syllabus of this course, it is time for us to conclude this particular course that we have been having for past several weeks. But the course will never be complete before I acknowledge the help and support that I have received from different corners to create this content for the course. First and foremost, I would like to put on record my appreciation for this NPTEL and the SIAM programs and my sincere gratitude for the Government of India for supporting these great initiatives. Having said that, I would also like to thank the administration of IIT Madras for providing all the infrastructural facilities to create this content. In fact, IIT Madras nurtures a dedicated team of NPTEL who are instrumental in creating all the video contents including this particular course. I am grateful to the entire NPTEL team for the wholehearted support that I have received throughout this course. And I would particularly like to mention my camera com editing crew, Mr. Vignesh, and my graphic designer, Mr. Rajesh Kumar. Last but not the least, I would like to thank all of you who have registered for this course. It goes without saying that without your participation, this course would never be complete. I hope you found the course useful, and I do look forward to receiving your feedback. So with that note, it is time for me to say goodbye. Thank you one and all.